This is the first video on complex numbers, and we're going to look at what they are, how to graph them, what the conjugate of a complex number is, and how to find the modulus of one. So what are they? Well, suppose you solve a quadratic equation and you use the quadratic formula. So you've done this. For AC over 2a, and this part here under the root, the b squared take 4ac, which is called the discriminant with the delta, turns out to be negative. Now that's a problem because you can't take the root of a negative number, and we say that the quadratic involved does not have any real roots. But it turns out that we can find some complex roots for that quadratic if we define a new type of number. And that type of number is the complex number. And it's defined as follows. The definition is that I squared is -1. That's where it all comes from. That's a definition. Basically that means you cannot understand this. It's a definition. It's just how it is. Now if I squared is -1, then we have a beautiful property that if we square both sides, I is going to be the root of -1. So now we have a solution for all the negative numbers that we want to take the square root of. See, in case this turns up negative, we can now do that. For instance, if you have the root of 4, well, everybody knows that's 2. But what if you have the root of -4? Well, now we know with the ordinary rules of roots that the root of -4 can be split up in the root of 4 multiplied by the root of -1. Now the root of 4 is 2 and the root of -1 is I. So the root of -4 is 2i, which is called an imaginary number, im. Complex numbers consist of imaginary parts, but also of real parts. Complex numbers are often written as z. So z is a complex number, which is sort of but then complex. Now the real part is often called a, and the imaginary part is often called b. And it's imaginary because there's an I attached. So this is the real part of the complex number. That's the imaginary part of the complex number. Together they make up the complex number. So for instance, we look at some examples here. A, z is 3 plus 2i. This is the real part, and that 2 there is the imaginary part. For b, 5i take 4. This is the real part. Oops, no. That's the imaginary part next to it. That's the real part. See? Z equals -2 over 3 plus the root 3 of I, root of 3i. The real part is right there. The imaginary part is right there. D, the third root of 11i plus the root of 23 all over pi. Well, the imaginary part is this bit here. So it's the third root of 11 over pi. The real part is over pi. There you go. Now what can you do with them? Can you graph them? Yes, you can. Graphing complex numbers. You see, normally you have a Cartesian plane like this with an x-axis and a y-axis. But now, this is not a Cartesian plane. This is not the x-axis. This is the real axis. And this is going to be the imaginary axis. So on the real axis, here's the number 1. And there's 2 and 3 and -1, -2, -3, very familiar. On the imaginary axis, this one is I. That's 2i, 3i. Here's -i, -2i, -3i, etc. And here's the origin. So plotting complex numbers is easy. 3 plus 2i is right there. So if that's a, then here it is a. 2 take I is there, that's point B. -3 take 3i is C, -3 take 3i, that's here. -4 plus I, -4 plus I is there, D. 3i is right here, E, and -2 is here, F. There they are. Now the beauty of this is that coming up? No, not quite, but a bit later we can say we can find the distance. For instance, the distance from the origin to that point A. That distance there is going to be called the modulus. Okay, now maybe we should go there since I mentioned it. So the modulus is the distance from a complex number to the origin, and you can view this as being a vector, an arrow. That's what we're going to do later, vectors. So the length of the vector is the modulus of the number. Let's have a look how that works. The modulus of a complex number is the length of it. Now the green modulus stripes there, modulus bars, like this. And basically what you do is you use Pythagoras. 3 and 2 squared, add them together and find the root. So in this case, the modulus of 3 take 4i is the root of 3 squared plus the root of -4 squared, which is of course 9, and 16 is the root of 25, which is 5. So this point has a distance of 5 to the origin. Let's skip to point C now. For C, -5 take 12i all over 13. If we want to have the modulus of that, we only have to look at the top because the bottom is a real number. So we're taking the root of 25 plus 144 all over 13. Now I can square the 13 and then root it, but it's still 13, so I don't have to do anything with the bottom, only with the numerator here. 25 and 144 is 169. The root of 169 turns out to be 13. So this point on the Argand diagram has a distance of 1 to the origin. Now that's the modulus. The last bit is what we call the conjugate of a complex number. Now if the complex number is z is given to be a plus bi in general terms, then the conjugate z star is a take bi. Now this is, it seems obvious, but this is very powerful because every time you find non-real roots on a quadratic or a cubic or a quartic function, if they are complex roots, they always come in pairs. And the pairs are always conjugates. So if you find this root of a quadratic, then this is also a root of the quadratic, the conjugate of it. That's why we need the conjugate, or one of the reasons why we need it. So let's do some exercise with it. Suppose you have a complex number z and you add the conjugate to it. What happens? Well, you have a plus bi and you add a take bi. What do you get? 2a. The imaginary part disappears. What if you subtract the conjugate from a complex number? Then you have a plus bi take a take bi. So the a's cancel out and the bi's double. So you only have the real part twice. What happens when you multiply a complex number by its conjugate? That's when you have a plus bi multiplied by a take bi. Feels like the difference of two squares coming up. So let's FOIL this, okay? A squared and take abi, and then this one plus abi. See, they cancel. The last one, interesting, bi times negative bi. A positive times a negative is a negative. So that's a negative b squared I squared. But guess what I squared was? I squared is negative 1, remember? So this turns out to be a plus b. So it's going to be a squared plus b squared. The difference of two squares, but it turns out to be the sum of two squares because it's complex numbers.